I should be able to teach the
texted me, Miss World does not understand
electromagnetism and quantum next year. Hopefully. We'll see. I mean, I hope that happens. There, once upon a time, engineering said that I would teach modern physics like the next year, and I was like, oh, okay. And then 10 years later, I was like, wait a minute, I never taught modern. What happened? So I don't know. You know, there are plans and there's reality. So, but anyway, it's just as well. Modern physics is boring as a course, not as a topic, but as a course. I don't like it. It's too hard to teach. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class. Just ask that you to guide our steps, help us to understand differentiation today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me get straight to the definition. So, so we're talking about differentiation. In normed linear spaces. And so let it be understood that V and W are normed linear spaces throughout this lecture. I don't want to write that again. Okay, so definition. Suppose U subset of V is open, right? And F is a mapping from U, which is a subset of V, to W. Here, V and W are normed linear spaces. Is a function grammar. Violet, why haven't you complained about the grammar here yet? Is a function, the we say. Maybe then, make that the then, that's better. Then we say that F is differentiable at A, an element of U, if and only if there exists a linear mapping L that goes from V to W such that the limit as h goes to 0 of big old square brackets on the top f of a plus h minus f of a minus L of h, all divided by h. Square brackets equals to 0. Now you guys tell me why that's wrong. Nope, that's not it. It is supposed to be from V to W. It's a linear map. It has to have a domain, which is the totality of the vector space. That's not non-negotiable. So, point of order, can we divide by a vector? It has to be the norm, right. So we have to put norm here. All right. If that's the case, in such a case, we call L the differential at A, and denote L equals to df sub A, right? If V is equal to R M, no. If V is equal to Rn and W, I'm going to change the definition a bit here. R equals to R, W equals to Rm. I mean, it's not wrong. It's just I like to put N in the domain and M in the codomain. Then the matrix of the differential is called the derivative of f at A. So like in particular, the standard matrix of the differential is denoted by f prime of A. In that particular context, if we're working with a mapping from real column vectors to real column vectors, that's the notation that we employ. And in that context, oh yeah, my notes are wrong. That M&M's got to be flipped in this definition, otherwise it's cuckoo for Cocoa Puffs. So then that would make it an m by n matrix, since it's, what that in particular means is that dfa acting on v is actually equal to f prime of a times v for all v in Rn. But this is the standard matrix. You guys know standard matrix, I hope? If not, talk to me. I'll explain it to you. It's not a big deal. So let me just take a breath here. What is this definition saying? This definition is saying that the function's differentiable if you can, in some sense, approximate. So let's introduce some terminology here. We can talk about change in f, right? Is f of a plus h minus f of a, right? So another way to look at this definition is it's saying that the change in f, right, at h minus L of h divided by norm of h goes to 0, right? In other words, it's saying that you can approximate the change in the function at the limit point by a linear function, right? In this sense. If it's possible to do that, then the function's differentiable at the point. Now, does this look like the definition of differentiable we saw in Calculus 1? Like not even remotely, right? So let us discover the connection with Calculus 1. Let's talk about that. So, suppose f is a mapping from, say, the domain of f, a subset of the reals, to the reals. And f differentiable at, let's say, x equals to a, right? Then we're given that the limit as h goes to 0 of f of a plus h minus f of a minus dfa of h divided by the absolute value of h is equal to 0. That's what it means in the Frechet sentence. By the way, this is I should mention, this is the Frechet derivative. I don't know where to put this thing. This whole thing is Frechet differentiability. There's also there's a competing notion of differentiability called the Gateau. I don't know how to say that. It's French. Differentiability. And I think in the infinite dimensional context, they might be different. But anyway, let's leave that for another course. The point is that this definition is a reasonable one if you're talking about differentiability on a Banach space, which is a pretty general concept. It doesn't even have to just be finite dimensional. Although almost every example I'll ever ask you, I should probably just say every example I'll ask you will be finite dimensional pretty much. It's going to happen. Huh. Interesting. So how do we get from this to the ordinary derivative? So this is the length of a vector in one dimension, right? So like, let's see here. Oh, there's a bunch of steps. Let me cheat and look at my notes here. All right, so of course we have that the absolute value of h is equal to either plus or minus h, right? And so just getting straight to the point, this is equivalent to saying the limit as h goes to 0 from the left or the right, right? Of f of a plus h minus f of a minus d fa of h divided by, okay, so how about that? If we think about left or right, should I put, I mean, I guess technically I could put a plus minus down here as appropriate, but think about it for a second. We could just put h here, right? Because if it's true with a minus h, it's still true with an h. So let me just drop the absolute value as we can do here. Yep.
Also, it's going to 0.
Yeah, because it's going to 0, I can do that, right? That's important. Is it Friday?
It's Get a Job Tuesday.
Oh, Get a Job Tuesday. So I was like, it's not formal Friday. What's going on here?
Yeah, I was
All right. So we can rewrite this as the limit as h goes to 0 from the right or the left. Or we're just, well, fine. So then we can just drop the plus. So long story short, what I'm really saying is we can drop the plus or minus and just look at this as a double-sided limit without the absolute value, right? So, and let me make another step. So we can say, oh, well, that's really a plus h minus f of a divided by h minus dfa of h over h. All right, that's equal to 0. I just did algebra, okay? Let's see here. But if we just focus on this piece right here, notice that the limit as h goes to 0 of 1 over h times dfa of h, what can we do there? What are we given? Well, we're given that the differential is linear, right? So I can pull the 1 over h inside. And that gives me what? Oh, wait a minute. Oh, I'm sorry, guys. Oh, well, yeah, that is what it gives me. Sorry, I was expecting to get 0 and I didn't, and it was kind of weirding me out, but I'll deal with it. So that gives me h over h, which of course is 1, right? Because the limit gets close to 0, but not equal to 0. You know the drill. So this is equal to the limit as h goes to 0 of dfa of 1, which is really just a constant, right? So that's dfa of 1. All of this to say that that limit exists, right? And it's a simple lemma that you can prove. If you have a limit of the, if you have a limit like this, if you have the limit as h goes to 0 of like a minus b equals to 0, and the limit as h goes to 0 of b exists, right? Then that implies that the limit as h goes to 0 of a has to be equal to the limit as h goes to 0 of b. All right, this is a elementary theorem of limits. You guys can prove it. You're welcome that I didn't make it a homework problem, right? You've had enough to prove about limits already. Let us not engage in this one. But it is a simple thing to prove, this lemma. Now, if the limit of b didn't exist, then this would not work, right? But the limit of b does exist. We just proved it's equal to dfa of 1. All right? Therefore, we have that the limit as h goes to 0 of f of a plus h minus f of a divided by h is equal to dfa of 1. What is that? Can you recognize what you're looking at?
F prime of a.
That is f prime of a, right. Calculus 1. This is the difference quotient definition of the derivative. So we have f prime of a is equal to dfa of 1. So, hey, apparently, if the function is Frechet differentiable, good news, it's differentiable in the sense of calculus 1. Wouldn't that be embarrassing if it wasn't the case, right? But no, it is the case. And so more than this, you can see that dfa of h would be dfa of 1 times h, right? So we've got h times f prime of a. Or if you like, you can write this in the confusing calculus 2 style way of like dy at a of dx is equal to, dy dx at a times dx, where they're putting the dx equals to h. I hate this. I hate this stuff with a perfect hatred. It's really bad. But that, in the sense of the definition I just made, it's kind of reasonable. If you're thinking about the h being a little change in x, it becomes reasonable. But anyway, so the matrix, the Jacobian matrix in this case, is the derivative. Identifying the 1-by-1 matrix with f prime of a. All right, enough about this. So that's the first thing, is it connects to regular calculus. Now, let's do another super easy example. I'll eventually get to not so easy examples. That was example 1, by the way. Example 2, suppose t from v to w linear, right? Then I would claim that the best linearization to t is t again, all right? So in other words, t, or if you like, the differential to t at a is just equal to t would be my claim. Does this work? Well, check it out. So if we have t of a plus h minus t of a minus dta of h divided by norm h, in this case, that's literally t of a plus t of h by linearity of t minus t of a minus, I'm claiming that we can just put dta, that's just t of h divided by norm h. This is very dumb. This is just what? 0 divided by norm h. So that's straight up 0 for norm h not equal to 0, right? So yeah, if you have a function which is linear, the best linear approximation is itself. Or in other words, the derivative of a linear function is the linear function again. A specific sub-example of this, how about the identity function? The identity function is a linear function from a vector space to itself, right? So this example is a sub-example of that. The differential of the identity at a point A is the identity. So the differential of the identity is the identity. How about a constant function? What should the derivative of a constant function be? I heard a 0. If we have f of x equals to, w naught for f, a mapping from v to w, then if you look at f of a plus h minus f of a divided by, norm h, so minus, you claim the 0 mapping works. I claim that you're right. See, because you get w naught minus 0 over norm h, which is equal to 0. So therefore, yeah, the differential of f at a is equal to the 0 map. Because the limit as h goes to 0 of 0 is 0. Yeah. All right. Let us do something that's not entirely trivial. All right. So let's look at something that we don't have any concept of how to differentiate in the calculus sequence, right? So this example is genuinely new. And so what we're going to look at is the function that goes from Rn by n to Rn by n, the square the matrix function. All right, let's look at that. So example 5. How about this? Let's let f be a mapping from Rn by n to Rn by n. All right, and where f of a is equal to a squared. So what do you guys think the derivative is here?
2a.
2a. I have a guess for f prime of a equals to 2a. Let's see if that works. So if we have f of a plus h minus f of a, what's that going to give us? So what I'm proposing here is we should calculate the change in f at a, and then from what we see, we should try to make an educated guess what the differential should be. That's the idea here. So how do you square a plus h? What have you done? You already changed it. Did you change? So did we ever see this?
Yeah, we saw.
We saw that? I want to believe.
I checked.
You checked him?
I saw the guy, your cameraman.
Well, I doubt the cameraman who intentionally at the end of Math 200 this morning failed to tell me that I said 0 was a natural number.
A squared plus 2 plus AH plus HA plus H squared.
So you were telling me something? I'm sorry.
A squared plus HA plus AH plus H squared.
So AA plus AH plus HA plus H squared. I almost did what you did. It doesn't matter which order. I mean, addition commutes. Multiplication, on the other hand, well, this is matrix multiplication, so you know it doesn't have to commute, right? So these A squareds, they'd be canceling, right? Those cancel. And it seems to me that this is the linear piece, right? So I'm going to make an educated guess. And my educated guess is going to be that d f a of h is going to be aha. All right. Let's see if it works. So we're going to calculate the change in f minus d f a of h, right, divided by norm of h. Let's see how that works out. So what I got by this above is that this is equal to, aha, plus h squared, right, minus aha, but with parentheses. See, Sam told me HA before AH, and I had to reject that. So, for my own personal reasons. So, of course, this and that be canceling. And what are we left with? We're left with h squared over the norm of h, right? Now we need to, in order to show that this function is differentiable with the the differential as claimed, right? We need to show that this limits to 0, right? So how should we do that? So here's how that goes. Let's look at the norm of the change in f minus dfa h divided by norm h. What can you tell me about that? So first of all, that's 0 is below it, right? Or equal to it, possibly. This is a norm, so it's bounded below by 0. And by the calculation that I have right above that, that's less than or equal to the norm of h squared divided by the norm of h, right? Which, by the way, we can pull out the norm because it's positive, right? And then that's going to leave us the norm of h squared. But thankfully, you guys proved the Banach inequality for the matrix case, or you're in the midst of it because you're going to turn in Thursday, but thank you. So we can rewrite this as h times h, right? But anyway, the point of that is that this simplifies to less than or equal to 1 over norm of h times the norm of h squared. That is a consequence of the more general identity. Norm of A times B is less than or equal to norm A, norm B, right? And if you're struggling with that, don't ignore my hint. My hint is life-saving if you understand it. If you don't understand my hint, talk to somebody else who's understood it. It's actually, this proof is like 4 lines long with the proper technology. It is hours and hours of suffering without. I've been down both paths. I know. Anyway, so this is what? This is the norm of H, which goes to 0, right? How do I know that that goes to 0? That goes to the norm of 0 as H goes to 0. What am I using there? Continuity, which we proved that the norm is continuous. So indeed, plug in 0. The norm of 0 is 0. So what I've then shown is I've shown that the norm of the Frechet, by the way, this is called the Frechet quotient. So I've shown that the norm of the Frechet quotient is 0, limits to 0, and then it follows then that this is a theorem, and yet another theorem. If you have the limit as H goes to 0 of like the norm of stuff equals to 0, then that means that the limit as H goes to 0 of stuff, I'll get it eventually, is equal to 0. So we're using that here. All right, another thing I should introduce you guys to is the linearization. What's the linearization? Do you guys remember that from Calculus 1? We talked about the linearization to a graph. The linearization to a graph is the tangent line at the graph, right? Well, the tangent line is the graph of the linearization. That much we can say. So definition, if f, from V to W is differentiable at A, then linearization of f at A of x, let's say, would be equal to f of A plus the differential at A of x minus A. That is the linearization of the function. And as I apologize for, well, I say it's this is the linearization of f, but I felt guilty about calling it the linearization because technically speaking, this is not a linear transformation. It's actually an affine function. So you could call it the affinization. I can't spell this thing. Affinization. It's the best affine function, best affine approximation to the function at the point. Let's capitalize on my example 6 and find that, actually calculate that for the square function, yeah? So example 6, find linearization for f of A equals to A squared at A equal to, what's a matrix that I like to calculate? The identity is good. And then, so let's do that. So we've got LF identity of x is equal to identity squared plus the differential at the identity of x minus the identity. All right, but what is that? So the identity squared is identity. And the differential at the identity is what? It's I. It's aha. So A is I here. So I go I. My H is x minus I. And then plus x minus I times I. I think it's 2x. 2x minus I. because I get a plus I, a minus I squared, but I squared is I again. So I think it's 2x minus I. Okay. It's kind of neat. So that would give you a way to approximate squaring a matrix. If that matrix is kind of close to the identity, that would be a reasonable way to approximately square a matrix. It's kind of funky, really. Anyway, any questions before I go on? All right, so this is the definition, and I have some, well, let's see here. I'm trying to decide what I want to, I'm going to hold off on the projector here for a bit. Let me prove a few more things. Oh, I'm an idiot. I just remember what I need to do. So there's more in the notes in terms of this direct kind of calculation, but after the dust settles, we really want to learn how to piece together the differential using directional derivatives. So I probably should at this point turn the page and start talking about directional derivatives. All right, so let's do that. And then I'll come back with the projector and pick up the pieces that I'm skipping over here at the moment. All right. So in particular, example 2.1.10 I think is really interesting. Make sure you look at that. The one we just did is the example after that. And oh, I actually do have, I thought I just made this up. I didn't realize it's in the notes. Sorry, I'm an idiot. So in the notes, the parts I'm skipping and we'll come back to here in a minute, is we can prove that the Frechet derivative of a sum is the sum of the Frechet derivatives. We can prove that we can pull constant outside the Frechet derivative. And we can also prove that we have a chain rule for Frechet derivatives. Like if you have a function, two mappings which are composed, the Frechet derivative of the composite is actually the composite of the Frechet derivatives of the respective maps. So we'll talk more about that in future lectures, because that actually, when you unfold what it means, it produces every single chain rule that you ever saw in Calculus 3. It's like all wrapped in this one chain rule for the Frechet derivative. But the directional derivative is what we should talk about in class here, because that's kind of, most of your homework is directional derivatives. All right, so a good bit of it anyway. So here's the definition. Suppose V and W are normed linear spaces of finite dimension. And I guess I don't really need finite dimension here, but well, anyway. And suppose the limit below exists for A in the domain of F, and V is an element of the vector space V, then we define the directional derivative of F at A to be d sub V F of A, which is an element of W as it happens, where dV F of A is equal to the limit as h goes to 0 of F of A plus HV minus F of A divided by H. Now, in some sense, let me just back up a second here, and instead of using h here, let me suggest I put a t there just to make us think about it being a real parameter. See, because this is not the same kind of limit we were just talking about, so maybe it's helpful for me to use a different letter just to kind of free your mind. This is a real parameter t, all right? So if I can just draw a picture to like schematically describe what's going on here, if this is a picture of V, right? We've got a point A, right? And we've got a direction vector V. And we're exploring, you know, values, like this is a typical point here, A plus TV, right? And so what this quotient is doing is it's studying the change of the function along this line in the vector space alone, right? It's a directional derivative. There's another way you could write the formula, and this assumes that you oh man. Well, I guess I don't have this in the notes, but you know, this could be written in terms of a derivative. What would this be in terms of derivatives? I guess this begs the question, do you know how to differentiate something like this, right? But supposing that you figured that out. If you did A plus TV, take the derivative of that with respect to time, and then evaluate at t equals to 0, that would be this directional derivative. Now, admittedly, I need to explain to you how we differentiate, take that derivative, right? But that's actually contained in the example I skipped over before the aha example, all right? So we'll come back to that, okay? I'll come back to like the calculus of this. It's not especially exciting. You do just what you'd expect. So we can calculate directional derivatives like that. Now, furthermore, if beta is, let's say, v1, v2, vn basis for v, then we can define partial f, partial x sub I at the point A to be equal to the directional derivative in the vi direction of f at A. Right. You know, here I'm assuming that x is equal to like x1 v1 plus x2 v2 xn vn. So like the x sub I are coordinate functions. Coordinate functions of beta. This would be what we mean by the partial derivative with respect to a coordinate on a normed linear space. It's the directional derivative in the direction of the basis. This exactly aligns with the definition of directional derivative that we gave you in Calculus 3. Almost. The one caveat is that I'm not saying that v has to be a unit vector. We allow directional derivatives for vectors of arbitrary length. So the directional derivative, unless you make a further restriction, doesn't have a direct meaning in terms of like the change of the function. All right? But nevertheless, we can calculate it. Now, it just so happens that if you're working with respect to an orthonormal basis, then the length of vi is fixed and given, and then this does have an objective meaning in terms of describing the change in the function, right? So, all right, what else I want to tell you here? We have a theorem, which I will project here in a moment. And the theorem says this: if f is differentiable at A, then df, then the directional derivative exists, and in particular, here's how it goes: dvf at A is straight up equal to the differential of f at A acting on V. So differentiable at A implies that all directional derivatives at A exist. But this is a one-way street. The converse is not true. It is possible to have all of the directional derivatives of a function exist, and yet the function fail to be differentiable. To get differentiability of the function, we face a multivariate limit. All right, we face a multivariate limit for the differentiability. It's a limit with respect to h going to 0, where h is a vector in a normed linear space, right? That's a very different kind of limit than this one. This is a one-dimensional limit, right? You remember in calculus 3, the drill, we can have all the one-dimensional limits for a function existing, and yet the multi-dimensional limit doesn't exist, right? Path limits and multivariate limits are different. You need some kind of continuity to paste together the directional derivatives. And we'll see next class, I'll prove that if your function has directional derivatives which are all continuous, then you can put them together and get differentiability. This is one of the major theorems of this course. It takes me about 20, 30 minutes to prove it. But all right, so now that we have this notion of partial differentiation, I'm going to do example 5 in a new way. Because, let me see if I can put things together here. So, okay, so let's think about, so we already know that the differential exists, right? So I think it's instructive to see how, like let's actually try to calculate the partial derivatives of this square function. So let's see here, example, what am I on? Oh man, what's that? 5.5? Is it 6, 7?
You did B6 last.
So this is 7. So let's look at f of a equals to a squared. And let me remind you that Rn by n has a equal to like a sum over I and j of aij, eij. In other words, the basis, eij, you know, that is basis, right? And so let's use the differentiation formulation. Let's calculate partial f, partial aij. So you notice that aij is a natural notation here for the coordinate functions on the n by n matrix, right? Those are the coordinates. So if we want to calculate partial f, partial aij, that is meaning I'm trying to calculate, one way to look at it is ddt of what? Oh, sorry. Brain stopped working momentarily. Oh, yeah. So A plus T Eij squared. And then we evaluate T equals to 0, right? So that's my f of T plus my f of A plus TV, right? So I'm putting that into practice for this example. My f is the square function, and I'm trying to calculate the derivative at A. My basis is Eij, right? So there we go. So I'm exploring how the square function changes if we move along the Eij direction in the space of matrices. Now, we can square that, right? So that gives me a squared plus what? Plus T A Eij plus T Eij A plus t squared eij squared. We've got to differentiate all that stuff and then eventually put t equal to 0. All right. So then what? All right, so this gives me a eij plus eij a. What's the derivative of a squared with respect to t? By the way, if you've had differential equation, you've done this kind of like calculus in differential equation, like differentiate matrices, no? But so that's 0. The t differentiates to 1, the t differentiates to 1, and that one gives me 2t eij squared, right? We're supposed to evaluate that thing at t equals to 0, so lo and behold, we get a eij plus eij times a. That's the partial derivative of f with respect to the aij. Now, so let's put it together. The differential of f at a, at h, right, is equal to, we can expand this. This is the differential at a of the sum of over ij, of hij, eij, right? Any vector, any matrix can be expanded in the matrix basis, but the differential is linear, right? So I can pull that out, and sum over ij of hij dfa of eij. But if you believe my theorem over there, right? This is really the directional derivative as well, right? This is the directional derivative in the eij direction of f at a, which is the same as what I've calculated over here, right? This is the directional derivative in the eij direction of f at a. That's the partial derivative. That's what partial derivative is. Partial derivative is a directional derivative. And as such, I can replace this with hij times my a eij plus eij times a from the calculation we just did over there. But then you can rewrite that as, a times the sum over I and j of, let me not write it down. Do you guys see what happens? Do I need to write more? These are numbers, right? So they can be brought in here. And on the other hand, they distribute over to there. And what do I get? I guess I'll write it out. You guys don't seem to. Pull the a out. Sum over I and j of hij, eij, parentheses, plus the sum over ij, hij, eij, parentheses, a, also known as a h plus h a. Do you see the difference in the calculational method here, though? Let me flip the script here for a second. Think about it this way. We could have calculated the partial derivatives of this function, right? And then if the derivative exists, it has to be able to be assembled by taking a linear combination of the partial derivatives in this way. And so we could have built the AHA function from the partial derivatives if we so choose. Now, I don't think that's the right way to solve this problem. I think example 5 is far more logically efficient. But I also like that we can actually calculate in terms of partial derivatives if we do so choose. Yeah. Okay, so at this point, my energy has waned. We must project. So, but the things I have to show you in the projection I think are rather beautiful. I think you're going to like them, hopefully. So you remember after we introduced differentiation in Calculus 1, what's the first thing we did? We took derivatives. we proved that the derivative of a sum was the sum of the derivatives, right? That's one of the things we did. We pulled constants out. We proved the chain rule, you know. Okay, we didn't prove the chain rule. We just said it was true, and you guys believed us. Some idiots might have proved the chain rule to talk to themselves because they don't know better, and still hold out hope that someday, once upon a time, there will exist a student who cares about the proofs. But, you know, some people. Not me, of course. We all make choices. Very nicely played, Preston. Nicely played. Let's see here. Circling back. All right. Let's see here. So the annoying thing is that was a lovely preamble I just gave for the sum rule, but the truth of the matter is that there's a couple of examples I should show you beforehand. Actually, let me just say a word about some things and not actually go through them. I just encourage you to read it. Let me describe to you what this example is. So this example, what is that? I can't read. Can you guys read the number for me? 2.1.6 is that one. I actually just look at a function from, you know, R2 to R2, I think, and I just directly calculate the difference and work through, you know, what is the Frechet derivative got to be at a point x comma y. And so I calculate the difference, I isolate the linear part, I prove that it's linear by observing that it's a matrix times the vector, and then I calculate the difference between the difference of the function and the linearization, and it works out to this. And then I give some simple arguments to prove that that goes to 0. All right. So read through it. It's a good example. Then I define the linearization, and I actually calculate the linearization for that same example. So look at that. It's a good example. There's probably a problem like that in your homework. We will eventually learn a better way to calculate. Like the start of next class, I will show you that essentially we can calculate partial derivatives to calculate the derivative. That's not especially useful for like example 5. This matrix example, from the definition, is the way to do it. But if we're talking about a mapping from like column vectors to column vectors, using partial derivatives to build the derivative is the way to go. All right, so we'll talk more about that next time, but because it's that big theorem I was talking about. This example here, 2.1.9, I look at a function which is going from, I think I'm missing, so I really should tell you that the domain is a subset of the real numbers. So what we're looking at here is a function from the reals to the complexes, right? This is, you could look at it as it's a function from the reals to the plane. So like in calculus 3, you talk about this as like a parameter, as like a space curve, a path in 2 dimensions would be what this is, for instance. Anyway, we're assuming that both u and v are differentiable functions. And my claim in this context is that the linearization, you can get it just from like basically adding the derivatives of those functions. And the I here is because of the context, we're complex valued. And so what I do is I prove that the linearization is linear. It's not especially exciting, but there's the proof. And then calculate the difference quotient. And in this case, it ends up being essentially the piece for u and the piece for v, but this is exactly the same mathematics we faced in the part I worked through at the start of class to show you that differentiable implies, if you really look at that argument, it goes both ways. Real differentiable in essential calculus 1, if and only if Frechet differentiable. That's a if and only if, actually, right? They're the same notion because of that calculation. And so if I know that u and v are differentiable, then I know that these limits separately exist and go to 0, and as such, the complex combination of them goes to 0, which is to say that this is a legitimate formula for the linearization in this case. This is really shouldn't be that surprising to you. The derivative of a space curve, we differentiate component-wise, right? Like if you've got r is x comma y, the derivative of r is x prime comma y prime. That's all this example is, except in the complex context. These are not complex derivatives, though. These are real derivatives. The complexity is in the codomain, not in the domain. if I want to describe to you what we mean by complex derivatives, that's another course, or what we'll do in 2 weeks. So, but we won't go as deeply in here as we do in complex, obviously. Oh, so sorry. So here's the grown-up version of that last example. Suppose you're looking at a function of a real variable into a vector space. So instead of having just 2 component functions, like my u and v from the previous example, now I've got n of them. g1, g2, g3, gn. N component functions, all functions of time, right? If that's the case, the differential of such a function, what do you think it is before I scroll down? For 2, yeah?
Some of the differentials.
Yeah, it's just the the sum of the differentials is the way we could look at it, like the vector of differentials, perhaps, something like that. Let's see the formula. So my claim is that, I guess you're right. It is the sum. You're right. Sum of differentials. Thank you. Well, that's the formula for the function. Where's my differentials? Right there, right there. It's right. You like it's right beyond where I got to. Yeah. If only they made like laser pointers that also had like scrolly things, but like Elon Musk. All right. So the differential of g. Yeah, I'm claiming it's the sum of the derivatives of the component function. So this is what I was just saying. Like if you have a path in space, x, y, z, the dr dt is dx dt, comma dy dt, comma dz dt. This generalizes that to a real valued, a normed linear space valued function from the reals. This is how you differentiate it. You can just differentiate component-wise. If those derivatives all exist, then the differential of such a function exists. And so this single example here and the calculus that I've kind of skipped over, it encompasses function r to r to rn, r to c, and even matrix valued functions of real variable r to rm by n. That's the kind of calculus that we were just doing. All right, so what that means then is that the theorems that I'll prove about differentiability will apply to that case, and in retrospect, we'll be able to apply those rules of calculus to make what I did here not just nonsense. So I actually will justify the calculus I did here in a in a kind of later circle back kind of way. Now maybe you don't care. Maybe you're just like, well, I understand how to do them, and that's enough for me. Just don't make me prove it. I respect that. I mean, until I ask you to prove it. But I probably won't. So we did this example. Great. And we did that. Great. So I need to introduce a little bit more language. And if I wasn't as tired as I am today, I'd actually write this out on the board, so my apologies. All right. It's not my best performance here. But we can set, this is my standard notation, eta sub f of h. What this is it's the difference between the difference of f and its differential. This is the Frechet quotient once you divide by the norm of h, right? So the Frechet quotient is this eta sub f of h divided by h. So this is just a nice label for the Frechet quotient for a given function. Notice that if we have differentiability, it is to say that we have this quotient goes to 0 as h goes to 0. But if we think about it, if h is not equal to 0 and the norm of h is less than 1, we also have this inequality here, right? And then by the squeeze theorem, this implies this goes to 0. If this goes to 0, that goes to 0. What's in the middle squeezes to 0 as well. So you see that not only does the quotient of eta sub f of h over norm h have to go to 0, eta sub f of h also must go to 0, of course, as well. So we have that the limit of the Frechet quotient, right, the limit of the numerator of the Frechet quotient must itself go to 0. And since and that means it's continuous, right? Because why is that? Well, the reason it's continuous, it would be continuous if eta sub f of 0 was 0. Is eta sub f of 0, 0? Well, eta sub f of 0, we plug it in here, right? So we get f of a minus dfa of 0.